Hello and welcome back. This is lecture 2 of the 3-part lecture series for the thermodynamic math labs. And on the PowerPoint we'll look at the topics that we'll be going over today. We're going to be looking at the ideal gas law, the pressure equation, average molecular weight, density, specific volume, heat, thermal equilibrium, work, Poisson's equation, and the hypsometric equation. And we'll start with the ideal gas law. The ideal gas law relates several variables, which are pressure, density, and temperature. And there is a gas constant within that equation also. There are several different ways that the terms can be arranged in the equation and ways to combine the terms to create new terms. For example, the density can be broken down into volume and mass, or the density could be written as specific volume instead. Next, we'll look at an example problem solving using the ideal gas law. Suppose the air pressure is 1,000 millibars and the temperature is 30 degrees Celsius, and we want to find out what is the density of this dry air. We're going to use RD as the gas constant since this is dry air. And when solving this equation, make sure that the temperature is in units of Kelvin. So if the units is given in Fahrenheit or Celsius, convert that to Kelvin. And the pressure must be in pascals. To convert millibars to pascals, you take the millibar value and multiply that by 100. So 1,000 millibars is equal to 100,000 pascals. So now we have the terms that we can plug into our equation to solve for density. The temperature in Kelvin is 273 plus the 30 Celsius that was given, and that will be 303 Kelvin. The pressure we determined is 100,000 pascals. So we're going to put our terms into the equation now, and our only unknown is density. So 100,000 pascals is equal to density times the gas constant times our temperature. Next, we'll multiply the 287 by the 303. That gives us that value of 86,961. And then next, we're going to divide both sides of the equation by 86,961 so that we have density just on one side of the equation. And once we do that, and divide those numbers out, the density is 1.15 kilograms per meter cubed. Next, we'll go to the overhead camera and look at how those units were derived. We had our pressure, that's in pascals, and that is force divided by area. Force is a Newton, which was a kilogram meter per second squared. So we're taking a Newton, which is force, and dividing that by area. So that's going to change this meters term to meters to the negative 1. So pascals, the units of that is going to be given in kilograms, meter to the negative 1 second to the negative 2. The joules per kilogram, which was, we divided that, we took the pascal and divided it by joules per kilogram. If we write a joule out, that's a kilogram meter squared per second squared. A joule is a Newton, which is here, times a meter. So that's why there's a meter squared there instead of just meter. And then our kilogram to negative 1. And then we divide these terms out and reduce. The kilograms are going to cancel out because they're both in the numerator and the denominator. The seconds to the negative 2 cancel out. The kilogram to the negative 1, we can take that from the denominator and move it up to the numerator to get kilograms. And the meter that's a negative 1, we can bring that down to the denominator, and that makes meters cubed. So that gives us our final units there of kilograms per meter cubed. So this is one way to check to make sure that you've done the math right if your units work out. And these are the units of density. Next on the PowerPoint, we're going to look at the pressure equation. This relates pressure, density, gravity, and height. And the equation is the pressure is equal to density times gravity times height. The density units that we found out are kilograms per meter cubed. Gravity is meters per second squared. Height in meters. The pressure is in pascals, which is a kilogram meter, -1 second to the -2. So if we multiply all those units out on the right-hand side of the equation, we are going to end up with the units in pascals. Pascal is kilogram meter to the -1 seconds to the -2. And in this equation, gravity is going to be treated as a constant of 9.8 meters per second squared. Next, we'll look at an example problem. Our problem is how much pressure is applied by the water of a 2-meter deep swimming pool. And it's given that the water has a known density of 1,000 kilograms per meter cubed. So next, we'll look at the equation and solve the equation. We're solving for pressure, so we do not know what the pressure is, but we do know the density. We know gravity since it's a constant, and we know H since it was given in the question. So the pressure is equal to the 1,000 kilogram per meter cubed density times 9.8 meters per second squared times 2 meters. And when that is multiplied out, that results in 19,600 pascals. And to convert that to millibars, divide by 100. So 19,600 pascals is equal to 196 millibars. So from that you can see that if you're in water, the pressure changes very rapidly going down underneath the surface of the water, where in the atmosphere the pressure changes more gradually since the density of air is much less than the density of water. The next topic we're going to look at is average molecular weight. And we went over in the last lecture how to find a weighted average, and we're going to have to do that for this example problem. For our example problem, find the average molecular weight of air that is 30% oxygen, 67% nitrogen, and 3% water vapor. We need to determine what the molecular weight is of each of these substances. Oxygen, which is O2, 2 oxygen atoms connected together, has an atomic weight of 32. The molecular weight of nitrogen is 28. And water, which is H2O, so that's 2 hydrogens, which are 1 unit apiece, plus an oxygen, which 1 single oxygen, which is 16. Add those together, that's 18 atomic units. So you can see from that that the water vapor has a lower atomic weight than oxygen and nitrogen. And that's the reason why if you add moisture to the air, it makes the density of the air a little bit less. And we're given that 30% of the air was oxygen, 67% nitrogen, and 3% water vapor. So we multiply these terms out to get the average molecular weight. So we take 0.3, which is 30% converted to a decimal. So that 0.3 times 32, since it's 30% oxygen and the molecular weight of oxygen is 32, those are when that term's multiplied together, that produces 9.6. The 67% nitrogen is 0.67 times 28, which produces 18.76. 0.03 for the water vapor times 18 is 0.54. And when those 3 terms are added together, they've been weighted now and added together, that produces a value of 28.76 28.9 for the average atomic weight. And when doing these problems too, once you derive at the final answer, see if the answer makes sense. In this case, the answer 28.9 makes sense. Most of this air is nitrogen, so it should be weighted more toward the 28 value, which it is in this case. Next, we'll discuss some more on density. Density is mass divided by volume. When the volume is constant, if you have a constant volume, the density is going to increase as the mass increases. So for example, if you have a volume of air and you replace that with the same volume of water, the water is going to have a much higher density because it has a much higher mass. When mass is constant, density will increase as the volume decreases. And this makes intuitive sense. If you take a volume and compress it, then the molecules within that volume are going to be getting closer together and thus are going to become more dense. We'll look at an example problem. Suppose the density is 3,500 kilograms per meter cubed, and the volume is 0.5 meters cubed, and we want to determine what the mass is of that. So our formula is the density is equal to mass divided by volume, and we want to solve for the mass. So we plug our knowns into the equation. The density of 3,500 equals mass divided by the 0.5 for the volume. And so we multiply both sides of the equation by 0.5 to have mass on one side of the equation. When that is done, we get a value of 1,750 kilograms. Notice that the meters cubed cancel out because there's a meter cubed in the numerator and the denominator. They cancel out. So we're left with just the kilograms for our mass. Specific volume. Specific volume is found by volume divided by mass. As we talked about last time in the last lecture, they're inverse. Specific volume is the inverse of density. Example problem, what is the specific volume when the volume is 0.004 meter cubed and the mass is 345 kilograms? So the specific volume is going to be our volume, 0.004, divided by 345 kilograms. And when those are divided out, we end up with a fairly small number here of 0.000111594 meters cubed per kilogram. Notice that the units are inverted from density units. And we can write that number in scientific notation. We move the decimal point to the right until we have a coefficient where there's only one number to the left of the decimal point. So we'll have 1.159 times 10 to the minus 5 meters cubed per kilogram. Heat. Heat is a form of energy, and the definition of heat is a transfer of energy from one body to another as the result of a difference in temperature or a change in phase. Next, we'll go over the concept of heat capacity. The definition is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius without change of phase. Units are also commonly expressed in calories per gram. So if the units are in calories per gram and you need to convert those to metric units, then you'll need the following conversions. 1 calorie is equal to 4.186 joules. And 1 kilogram is equal to 1,000 grams. The specific heat of water is fairly high. It's 1 calorie per gram, or 4,190 joules per kilogram. So it takes 400 4,190 energy units in joules to raise the temperature by 1 degree Celsius when given a kilogram of liquid water. Ice has a somewhat different value of specific heat. It is 2,000 joules per kilogram. So for water, it takes a larger amount of energy to raise the temperature by 1 degree Celsius. And by comparison, here are some other substances and their specific heat, which are much lower than liquid water. Aluminum, 910, copper, 390, lead, 130. Those metals there, since they have a lower value of specific heat, it does not take as much energy to warm them up. So if you put the same amount of heat into aluminum as you did the water, the aluminum would warm up much faster than the water would. Water is slow to warm up and slow to cool compared to many other substances. Next, we're going to go over thermal equilibrium. Thermal equilibrium occurs when one or more substances in a system have the exact same temperature. They may have different temperatures, but once they're in contact with each other and the heat has transferred, then over time they'll have the same temperature. The amount of heat transferred depends on the temperature difference and the heat capacities of the substances. There's an equation for thermal equilibrium, and this equation should be given in the book, and there's some explanation on it there, but I'm going to go into more detail in this lecture. The M in that equation is for mass, and the C is for the heat capacity. So the amount of heat transfer is going to depend on the mass of the substances that we're dealing with, the heat capacity of each of those substances, and then the temperature difference. The TF is the temperature once thermal equilibrium is reached, and T is the initial temperature of the substance. The equation at the top, you'll notice that the third term has mx plus cx there. The x denotes that there's an unlimited amount of terms you could have. There could be 2 terms in the equation. In that case, you just have M1, C1, and M2, C2. But if you had 3 substances coming into equilibrium, then you'd have an M1, an M2, and an M3, and a C1, a C2, and a C3. Or you could have 4, 5, or more substances. Next, we're going to look at an example problem. And here's our example problem. Assume heat is contained in a closed system. We have 10 kilograms of water at 1 degree Celsius, and that is poured into a 5 kilogram copper vessel that is much warmer, and it's at 50 degrees Celsius. And we want to determine what is the temperature at thermal equilibrium of the system. So the water is much colder than the copper vessel is. So we know intuitively that the water is going to warm up and the copper vessel is going to cool down. And there's some temperature that they're going to reach over time in which they'll come to thermal equilibrium and have the same temperature. And what we want to determine is what that temperature is. So on the overhead camera, we'll take a look at solving this problem. We have 2 terms. We have the water and we have the copper vessel. So there's only 2 terms that we need to deal with. So we have an M1 and M2 and a C1 and a C2, and for both of them we have the temperature after thermal equilibrium minus the initial temperature. First, we'll look at M1 and C1. The M1 was 10 kilograms, and this was the water. We had 10 kilograms of water. The C1, this is the heat capacity of water, which is 4,190 joules per kilogram. and then TF, which is what we're trying to find. This is the temperature at thermal equilibrium, then minus 1, and this 1 comes from that the temperature of the water is 1 degree Celsius. Now for the M2C2 term, the M2 term, we had a 5 kilogram copper vessel, and the C2, the specific heat of copper, is 390 joules per kilogram, and that's multiplied by the temperature at thermal equilibrium minus 50, where this 50 results from the initial temperature of the copper vessel was 50 degrees Celsius. So we solve this equation out now. We take the 10 and multiply it by the 4,190. That gives us 41,900 times TF minus 1. The 5 times 390, that gives us the 1,950. And we can simplify further by multiplying this term here by the first term and then by the second term. When that's done, we have 41,900 TF minus 41,900, since 41,900 times 1 is 41,900. On our next term here, we multiply these two terms out, and we're left with 1,950 TF minus 97,500. Now we can group the like terms together. We have two like terms here that are just numbers, and then we have two like terms that both have TF in the equation. So we're going to group those like terms together. So we take this 41,900 TF and add it to this 1,950. That produces this value of 43,850 TF. And what we're going to do is we have the equal sign here, and we're going to take these two numbers to the other side of the equal sign. So they're going to change signs. So instead of being negative numbers, they're going to be a positive number, which once it's moved to the other side of the equal sign. So we have 43,850 TF is equal to 139,400. And we divide both sides by 43,850, and that gives us our final answer of 3.2 degrees Celsius. So since the specific heat of water is so high, it doesn't warm up very much. The copper vessel cools down significantly while the water just warms up by a modest amount. Next on the PowerPoint, we're going to look at work. Work is equal to force times displacement. And there's two ways there that work is written. Work is equal to force, which remember force was in newtons, times distance. Distance can be written as a displacement, or ds, where ds means a change in distance. It can also be written as the change in work is equal to the pressure times the change in volume. And we'll look at a basic problem next here. A 50 Newton force pushes a couch along the floor 6 meters. How much work is done? To solve this, we multiply the force times distance. So we have 50 newtons times 6 meters is equal to 300 Newton meters. The units of work are in joules, so we have 300 joules. Next, we're going to look at a very important equation in meteorology. This is Poisson's equation, and it is used to find the potential temperature, which you'll often see it denoted as the term theta. So if you're reading a forecast discussion and it mentions theta in there, that's a reference to potential temperature. Well, what is the definition of potential temperature? The potential temperature is the temperature of a sample of air. Think of a parcel of air somewhere in the atmosphere, and we take this parcel of air and we bring it down to the 1,000 millibar pressure surface at the dry adiabatic lapse rate and read off what the temperature value is. Remember, any time that air is sinking in the atmosphere, it's going to warm at the dry adiabatic lapse rate, which is about 10 degrees Celsius per kilometer. Next written there is the Poisson's equation, the potential temperature equation, PT. It is solved by taking the temperature, and that temperature has to be converted to kelvins, then multiplying that by 1,000 divided by P, where P is the initial pressure of the parcel, and then that's raised to the RD divided by CP, that's the power. And so you're going to need the scientific calculator to solve that out, because you're going to find a number there once you take 1,000 divided by P, and then you have to press the X to the Y button on the calculator, or the power button on the calculator, raise it to the 0.286 power, and then multiply all that out by the temperature to determine what the potential temperature is. So the constants that are in the Poisson's equation are the gas constant for dry air, the 287 joules per kilogram per Kelvin, and CP, which is a constant pressure process, 1,004 joules per kilogram per Kelvin. Next, we'll look at an example problem, and I've written the equation there for a potential temperature again. What is the potential temperature of a parcel of air at the 800 millibar level that has a temperature of 10 degrees Celsius? So we're at 800 millibars, we have a parcel of air. It has a temperature of 10 degrees Celsius. We're going to take that parcel of air and bring it down to the 1,000 millibar pressure surface. And we want to find out what the temperature of that parcel of air is going to be once it reaches 1,000 millibars. On the overhead camera, we'll take a look at solving this equation. So we have our theta, potential temperature, is equal to the initial temperature, which must be in Kelvin. So it was 10 degrees Celsius, so we add 273 to that value. So that is a value of 283 Kelvin. And our initial pressure is 800 millibars. I've mentioned that usually the pressure in equations is going to be written in the units of pascals. But in this situation, it doesn't matter whether it's in pascals or in millibars, because you're simply finding what the ratio is of those two numbers. So even if you wrote both of these numbers in pascals, by multiplying each one of them by 100, you'd still end up with the exact same number. And actually, what's inside the parenthesis here, the units cancel each other out, and you'll be left with a number. So we have 1,000 divided by our 800 pressure, and that ratio is 1.25. So we need to take 1.25, and on your scientific calculator, raise that to the 0.286 power. And I'll do that on this calculator here to get a number here, for what you can expect. 1.25 to the 0.286 power. So you're going to get a number that's a little bit bigger than 1. It's going to be about 1.065 with some more digits after that. So if you get a number that's a little bit bigger than 1, then you've done it right on your scientific calculator. And then you take this value that you just calculated and multiply that by our 283 degree temperature. And once that is multiplied out, we have a temperature of 301.6 Kelvin. And potential temperature, when you have the final answer, it's always written in units of Kelvin. On the PowerPoint, the next topic that we're going to look at is the hypsometric equation. This equation is used to measure the distance between two pressure levels in the atmosphere. So for example, finding the 1,000 to 500 millibar thickness is going to use this equation. The thickness is primarily a function of the average temperature between two pressure levels. And it's a secondary function of how much moisture is in that air. So moisture is combined with temperature to produce what is known as the virtual temperature, which will be gone over in another lecture. So thickness is a direct function of the average virtual temperature between two pressure surfaces. While, as I mentioned, within that virtual temperature, the actual temperature is the most important contribution to determining what the thickness value is. Next, we'll look at the equation for the hypsometric equation. When you see a capital Z, that refers to thickness. So the Z2 minus Z1, that is a change in distance in the vertical, which is a thickness. And that is equal to RD, which is a constant, times TV, which is the virtual temperature, divided by gravity. And then once that value is determined, that is multiplied by the natural log function. And we went over that in the last lecture, how to solve the natural log function on the calculator. So that's that LN button on the calculator. So you take the P1 and divide by P2, and that'll produce a number. And then you take the natural log of that number and then multiply it by RD times TV divided by the gravity. So I mentioned the TV is the average virtual temperature, and it's in kelvins. Again, the temperature has to be written in kelvins when solving this equation. And the virtual temperature is going to be slightly higher than the actual temperature. The P terms in the hypsometric equation, the pressure at the base, or the bottom of our layer, is the base, and the top of the layer is the P2. So suppose you wanted to know the thickness between 700 and 850 millibars. The pressure at the base, P1, would be the 850 millibar, while the pressure at the top, P2, would be 700 millibar. The two pressures are divided by each other, then the natural log function is taken of this value. So if you take 850 and divide that by 700, you'll get a number of 1.214 and some other digits. And then once you press the natural log function, that produces a value that's given there of 0.194156014. And when solving this equation, make sure you don't round any of the terms. Keep the number written out as many digits out as the calculator will give that to you. Don't do any rounding until you have the final answer. So this is just an intermediate step in solving the hypsometric equation. So don't round that number 0.194 with the rest of the digits. Gravity can be treated as a constant, the 9.8 meters per second squared. Next, we'll look at an example problem. We're going to find what the 1,000 to 500 millibar thickness of the air that has an average temperature of -2 degrees Celsius and an average virtual temperature of 0 degrees C. So this is to show you an example that the average temperature of the layer is not going to be too much different from the virtual temperature. The virtual temperature will be just a little bit higher because it's taking into consideration the moisture in the air. And on the overhead camera, we'll take a look at how to solve this equation. Thickness is denoted with Z, and you'll want to write all this information down. What I have here at the top is our knowns. We know that the P1 value is 1,000, so the bigger number is going to be on the top. And the P2 is 500. So there's our ratio between P1 and P2, is 1,000 and 500. Our temperature that was given, the average virtual temperature was 0 degrees Celsius. We need to convert that to Kelvin, so we add 273 to 0, and so we have our temperature. So we have all of our knowns that we need to plug into the equation to solve for Z. Our RD value is 287 joules per Kelvin per kilogram. It's the gas constant for dry air. And then we multiply that by the average virtual temperature, the 273, and divide by 9.8. Then multiply that by the natural log of 2. That 2 came from taking 1,000 and dividing by 500. So that gives a value of 2. So in your scientific calculator, you'd put 2 in and find what the natural log of that number is, and this is what you'll get. You'll get the 0.693147181. And that is multiplied by 287 times 273 divided by 9.8. And when you solve those numbers out, you'll get 1,000 to 500 millibar thickness of 5,542 meters. What I've shown in this area here is how the units are derived. I've taken all the units that are given there and canceled all the units out, and you'll be left with the units of meters, which makes sense because thickness is a distance in the vertical, the distance between two pressure levels, and that's going to be in meters. Now on the PowerPoint, we're going to look at some example problems. So this is our Thermodynamics Math Quiz 2. And just as you did in the last lecture, you're going to want to write down these 3 questions that are being asked. Question 1, what is the temperature of dry air that has a density of 1.4 kilograms per meter cubed at a pressure of 1,500 millibars? Question number 2, what is the water pressure at the bottom of a 5-kilometer ocean trench? And use the density of seawater of 1,027 kilograms per meter cubed. Question number 3, what is the average molecular weight of dry air using only the 3 most abundant gases? And on the overhead, I need to give you some information for number 3. And here is that information that you're going to need. So you're finding the average molecular weight of dry air using only the 3 most abundant gases. And here are the 3 most abundant gases. You have nitrogen, which is 78% and 28 atomic units. Oxygen, 21%, 32 atomic units. And then argon, 1%, with 40 atomic units. So you're going to need this information here to solve for number 3. And we'll go back to the PowerPoint. You want to write these 3 questions down and then stop the tape and then solve them the best you can and then turn the tape back on and we'll go over the answers. Okay, here are the answers for the first 3 questions, and we'll look at each solution on the overhead. And we'll start off with question number 1, which we were asked, what is the temperature of dry air that has a density of 1.4 and a pressure of 1,500 millibars? So the units have to be in pascals. So we're given a millibar value. We need to multiply that by 100 to get that in pascals. So that's 150,000 pascals. Our density is 1.4 kilograms per meter cubed, and our gas constant is 287 joules kilogram per Kelvin. So we have all our unknowns in the equation, and we just need to find what this temperature value is. So we take 150,000 pascals and divide by 1.4 and divide by 287. And that will give us a value of 373 Kelvin. And then below here, I have written out how these units work out. So we had pascals, which this 150,000 here was in pascals, and we had the rest of the units here, which we divided by the pascals, which is given down here. And then we reduce these units out, and once we do that, we're going to end up with units of Kelvin. So the kilograms cancel each other out. There's a second to -2 that cancels out. Here's a kilogram times 1 over kilogram. Those are going to cancel out. We got meter to the -3 times meter to the -2. That becomes meter to the -1, and that'll cancel with this meter to the -1 up on the top. So we're left with just 1 divided by Kelvin to the -1, and we can just bring that up to the numerator, and it changes sign, and we're just left with Kelvin. The second question, we were asked for that pressure at the bottom of that trench. So we want to use the pressure equation. Pressure is density times gravity times height. We had density of seawater of 1,027 kilograms per meter cubed. We have gravity 9.8 meters per second squared, and our H was 5 kilometers. So we need to convert that to meters to go along with the meters that we have in our other terms. To cancel the units out, they need to be in the same type units, whether that be mass or distance or temperature. So that is 5,000 meters. So now we have all the terms that we need to find our pressure. The pressure is the density times the gravity times the height, and that produces a very high value in pascals. Of course, have a deep layer of water that has a very high density, so we're going to get an extremely high pressure at the bottom of that trench. So we have over 50 million pascals. We can divide by 100 to get that value into millibars, 503,230 millibars, and we can divide that by 1,000 and express it in bars. We have 503 bars. And here's some information on the units. The pascals, the kilogram meter, the -1 second to the -2. 100 pascals is 1 millibars we've gone over, and 1,000 millibars is equal to 1 bar. For number 3, you're given that information at the top there already. And so we need to find an average weight of those values. So we got 78% nitrogen times the 28, because the 28 is the average molecular weight of nitrogen. Add to that 0.21, which is the percent of oxygen times the 32, and add to that 0.01 times 40. And when these 3 terms are found and added together, you'll get a value of 28.96 atomic units. I have 3 more questions for you on the PowerPoint. You want to write these down. Question number 4, 10 kilograms of water has a temperature of 41, 7 kilograms of water has a temperature of 50. What temperature of the system results when the 2 water samples are mixed together? Number 5 is find the potential temperature of a parcel of air at 750 millibar level that has a temperature of minus 15 Celsius. And number 6, what is the 850 to 700 millibar thickness of air that has an average virtual temperature of 10 degrees Celsius? So write all that information down. Hopefully you have all your notes, the lecture notes, so you can attempt to solve these 3 questions here, and then stop the tape. And then when you're ready to check answers, then start the tape back up. Okay, we'll go over the answers now to number 4 through 6. And we'll start with number 4, determining what the value of that temperature is once those water samples are mixed together. So we'll go to the overhead camera and see how that is solved out. So we had 10 kilograms of water, that was 41 Fahrenheit, and we need to convert that to Celsius. So 41 Fahrenheit is 5 degrees Celsius. And then we had 7 kilograms at 50 degrees Fahrenheit, which is 10 degrees Celsius. And the water has the heat capacity of 4,109 joules per kilogram per Kelvin. Notice that we use Celsius and Kelvin here, but that's okay to use the Celsius in the equation because the increment of a temperature change in Celsius is the same that it is in Kelvin. And next we have our equation that we looked at earlier with our M1, C1 terms. In this case, C1 and C2 are going to have the same value since they're both dealing with water. The only difference is that they have different masses and different temperatures. So our M1 is 10 kilograms, and multiply that by the 4,190 times the final temperature minus the 5 degrees Celsius. Then add to that the 7 times 4,190 times the TF minus 10. And then we multiply these 2 terms together to get the 41,900, multiply these terms together to get the 29,330, and then we distribute the term to each of the terms in the parentheses. And once we do that, we'll have 41,900 TF minus 209,500 plus 29,330 TF minus 293,300. And we're going to group the like terms. We have 2 terms that are just numbers. We're going to put those on the right side of this equal sign. So they're negative here, but they'll become positive. And when those are added together, that'll be 502,800. We'll add the TF terms together. That produces 71,230. And we divide each side by 71,230 to get our final temperature, which is a little over 7 degrees Celsius. And if we convert that back over into Fahrenheit by using the 9/5 C plus 32, we'll get a temperature of about 45 degrees Fahrenheit. So in our calculator, I'll put in the 7.06 times 9 divided by 5, and then add 32 to that, and that produces a value that's almost 45. It's almost 45. If we rounded it to a whole number, it's 45 degrees Fahrenheit. The next question asked for the potential temperature. So we'll look at that next. The potential temperature equation is the temperature times 1,000 over P to the 0.286. We were given a temperature of minus 15 degrees C, and in this equation that has to be converted to Kelvin. Potential temperature is always expressed in Kelvin. So we take 273 minus 15, and that produces 258 Kelvin. So 258 Kelvin is our temperature. Our P was 750 millibars, so we have 1,000 divided by 750. We'll get a number there. And then we raise that to the 0.286 power, and that'll produce one number on our calculator, and then multiply that by the 258, and that'll give a value of 280 Kelvin for the potential temperature. And our last question dealt with finding the thickness value. So the equation that we need is thickness is RD over TV over G times the natural log of P1 over P2. Our P1 and P2 terms are 850 and 700. The bigger number, remember that when solving this equation, the bigger pressure number goes up on the top. So you have 850 divided by 700, and we take the natural log of that value. So 850 divided by 700 equals 1.2 and some other digits, and we take the natural log, and that gives us that 0.19415. As I mentioned, write all the terms out because you don't want to do any rounding until you get to the final answer. And then we multiply that by the 283, and then multiply that by the 287, and then divide by the G value, which was 9.8. Again, the 283 here came from our average virtual temperature. We were given that it's 10 degrees Celsius. We added 273 to get that 283 Kelvin. And then this 287 is just the gas constant. 9.8 is the gravity. So once we multiply and divide out all these terms, we're left with 1,609 meters for the thickness value between 850 and 700 millibars. So we go back to the PowerPoint here. We'll see that we have reached the end of our lecture for today. So we have finished